Hello everyone, and welcome back to this series on financial mathematics. And today we're going to be taking a look at a new financial product known as a bond. Now, bonds have very similar structures as to loans, so I want to start off with a brief review of loan structures. So what is a loan? So a loan is where we borrow X dollars, say 25,000, and then we make monthly payments, M1, M2, M3 down to MN for a series of M payments, for example, 6 years or 6 times 12 months, right? So that would be your transaction history for a loan, for example. So what does that exactly mean? So that means we borrow or we gain X dollars at time t is equal to 0 and pay or lose MK dollars at time t is equal to k. In total, obviously that would be equal to the sum from k is equal to 1 to n of these transactions, MK, right, our monthly payments. Now, bonds follow a similar story. So here's going to be a timeline for bonds. Let's again draw our timeline. So we're going to go from t is equal to 0, 1, 2, 3, down to n minus 1 to n. Now what we're going to do is we're going to be losing F dollars at time t is equal to 0, and we're going to be making C1, C2, C3, down to Cn minus 1, down to Cn, and also R at time t is equal to n. So it's almost like a mirror image to the transactional structure as that of a loan. So now let's go ahead and define some of these structures that bonds are going to be using. So what exactly are bonds to begin with? So we're going to have two main parties in this conversation. We're going to have bond holders, that's going to be us, and then we're going to have bond issuers. So what's going to happen is we're going to invest or lend F at time t is equal to 0 to our bond issuers. And what the bond issuers are going to do is going to give us a bond, which is technically, I guess, equivalent to an IOU, right? So they promise to pay us money sometime into the future. So this value, F, so F is sometimes referred to as the face value. Some people also use the phrase par value of the bond. And these payments, CK, are sometimes called coupon payments. Coupon payments. Sometimes people will also view them as interest payments. That is, we're getting interest over some period of time of the bond. And this last value on our timeline that we drew out was R. This is sometimes referred to as the redemption or the maturity value of the bond. Okay. Now, a couple clarifications that are common in bond structures. The coupon payments are typically small and level, so almost like an annuity immediate or an annuity due, and they're usually small, like $5 compared to like $5 billion. And the redemption value is typically equal to F. If R, the redemption value, is equal to F, we usually refer to that as a redeemable at par bond, or a bond that's redeemable at par, or a par bond. So a bond redeemable at par. That is, they're just going to write you a check for the amount of money for which they borrowed, in addition to paying you these series of coupon or interest payments over some period of time, right? So let's again take a look at our timeline just to make sure we understand. So 0, 1, 2, 3, all the way down to m minus 1 and n. So we're going to make a payment or we're going to receive a payment C1 at 1, C2 at 2, C3 at 3, all the way down to Cn minus 1, and then Cn at time t is equal to n. But we're going to lose our face value at time t is equal to 0. So we're going to be lending out money at time t is equal to 0. That's equivalent to the company borrowing money from us or taking out a loan from us. And in addition to these little interest payments, which were usually small, because once this goes to the bank or the business that we're lending it to, they need to use that money for something. So they can't just give us a large amount of money back in the near future. And that's why at time t is equal to n, they give us back a lump sum called a redemption value at time t is equal to m to sort of make up for the value f and then some, usually sometimes more, not usually, but sometimes more, to make up for all of the interest that you may have lost on that investment F that you could have made with other investment strategies into other financial products. So to determine the value of C, so typically, but not always, there are a couple of variations, C is constant. So we're going to be assuming that C is constant for the basic, but technically speaking, it need not be. So if C is constant, usually C is going to be equal to a proportional value of the face value. Some people will refer to this RC as the coupon rate. Also want to note, some people will use C as the redemption value and R as the coupon value. As to why, there are a couple of reasons why, which I'm not going to get into, but make sure that the notation is consistent with whatever context you wish to advertise these concepts with. Right? So we have C, our coupon payments, are going to be equal to some small percentage of the face value. Another concept that is going to be extremely useful to us is referred to as the book value of the bond. And we're going to be looking at, for the time being, only the present book value of the bond, usually when you buy it. And this is going to be represented by BV, similar to PV for present value. So BVT is equal to 0, and then we're going to superscript this with the interest rate under consideration. So what is that going to be? So keep in mind, our payments are going to be of the form C, 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 C down to C, and then C, and then R times t is equal to n. So you could view R as maybe a differential balloon payment. So what would the present value of this be equal to? So that's going to be equal to C times the present value of a unit annuity immediate, and then a discounted value of R n times. All right, so this is what we refer to as the present book value of the bond. Okay, so what else do we have? A couple other terminologies that might be useful to know before we actually get into the math and the conceptual discussions is the price. The price P of a bond is the amount a party agrees to pay for this bond from another party. Now, you might be thinking, well, why is there this concept of price? Don't we already own the bond? Well, not necessarily. So let's take this example, for example, so somebody invests, say, $500 to this company, and they're not going to be getting coupon payments for like a year, for whatever reason. And then they're going to be starting to get coupons here, 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 and here. And let's assume that those constant payments are equal. And then at time t is equal to n, let's assume they give you both a coupon payment and $500. Let's assume by the time we get here, this person who owns this bond doesn't want to have this bond anymore. So keep in mind, they're already down $500. So it's possible that you might want to buy this bond from this person who holds it, this bondholder. So maybe we could pay, I don't know, $450 to them. Then they're only down $450, or they might upcharge it to maybe $550. But keep in mind, as far as you're concerned, this value and that value should be comparable to some degree. So if you pay $500, keep in mind you only need to wait 2 periods until you start getting your coupon payments, and then you can wait your N-2 periods until you get your reimbursement of $500 at the very end, right? So that's why this concept P is part of this discussion, because the bonds could be owned by other people and you might want to purchase these bonds from bond holders or potentially bond issuers as well. So in addition to price, let's assume that P is equal to the book value at time T is equal to 0, J, right? So now notice that we have a price P that's chosen by us, and then we have this book value BV, which keep in mind is just going to be equal to our coupon payments times A and J, and then plus our R times nu J to the power of M. So we have this particular equation. Now keep in mind, this P could be generated with respect to our effective interest rate over time, or this P could be chosen by us for some other random reasons. That's why this interest rate is not necessarily equal to the effective interest rate. And also keep in mind that these effective interest rates might be changing over time, right? So this rate J is not necessarily equal to the effective interest rate. So what is this rate J? So J is called the yield rate. The yield rate. Some people also call it the effective yield. Effective yield of the purchase or of the bond purchase. All right? And all it comes down to is just solving that equation for J. So let's just write this equation out to sort of see what that solving for J actually looks like. So we're going to have P is equal to, so that we're going to have C divided by J, multiplied by 1 minus 1 over 1 plus J to the power of M, and then plus R over 1 plus J to the power of M. So notice that J is located in that rational function there. Then we have an nth degree rational function here and here in 2 different places. So usually what you would like to do is solve this equation via graphing, but there are some advanced analytical methods that can give you close representations as to find J directly if I give you what C, R, P, and N are all equal to. But there are a couple graphical things that you should definitely understand when it comes to these matters. So the first thing that I want to look at is the effective interest rate versus the present value of an annuity immediate. So you should already know the equation for ANI. So keep in mind ANI is just going to be equal to 1 over I times 1 minus nu to the power of n. As n goes to infinity, nu to the n goes to 0, so you're just going to be left with 1 over I. So it's definitely going to be decreasing. So if you look at this curve, as you increase the value of I, the present value of ANI will decrease. So that means as I increases, the present value of the annuity immediate decreases, right? It's worth less over time. And if you take the formula for P and look at it as a function of our yield rate J, you're also going to get this curve as well. But instead of this particular perspective, instead of saying as J increases, the price decreases, what's actually more useful is to consider what happens as J goes to 0 from the right-hand side. So as J goes to 0 from the right-hand side, notice that the curve is going to be going up. So as the yield rates go down, bond prices will go up. And this is going to give us a few things for strategies for buying or potentially selling bonds. So therefore, what can we conclude from that? So a bond you buy at a cheaper price will provide a higher return on investment. Right? Assuming everything else is held constant, of course, right? So a bond that you buy at a cheaper price will provide a higher return on investment. Some people also use ROI to abbreviate return on investment. So those are just a couple things, terminology-wise, that you definitely should know with bonds. Now let's actually go through a calculation example to sort of make sure we understand the inner workings of these formulas. Suppose we have a bond that's up for consideration to be purchased by us, or maybe we already own this bond. And let's assume that the face value of this bond is $500 with a coupon rate of 2.1% that's fixed, and then a redemption value of $800 with fixed monthly coupons at the end of every month for a duration of 2 years. So the bond will mature after 2 years. And let's assume that the effective interest rate for all time t in between those 2 years is a fixed 1.9%, just to make the math a little bit more easier to deal with. So what will our coupon payments be equal to? So our coupon payments are going to be equal to our coupon rate multiplied by the face value of our bond. So that's going to be equal to 0.021 multiplied by our $500, and obviously this is going to be in the unit of dollars, and this is going to be equal to $10.50. So we're going to lend $500 to somebody, and they're going to give us these $10.50 payments at the end of every month, since they're using our money, and hopefully they're making more than $10.50 on the $500 for which they gave them. So let's actually build a timeline just to make sure we see that. So 1, 2, 3, all the way down to n, which is going to be 24. So we're going to have our 1050 there, our 1050 there, our 1050 there, our 1050 there, and our 1050 there, in addition to our 800 redemption payment, and time t is equal to 24. So a couple questions you might be thinking. Our face value was 500. Why would the redemption value be 800? Right, so let's actually consider that. So why would our redemption value be bigger than face value? Because didn't you mention, Nemo, that the redemption is typically equal to the face value? Yes, this is the case. So maybe they anticipate large interest rates. Or one thing from the consumer perspective, because to us, they're like, oh, wow, the redemption value is higher than the face value. That means this bond is worth more today, right? So that means they could be desperate. They could be desperate for investors, right? So they're desperate for investors. So for consumers, that's really good for us, right? So that means they can sell a lot of bonds, actually, because keep in mind, we're losing 500. So as long as they choose a redemption value that's more than 500, for example, 550 or 600, that makes these bonds a lot more appealing, assuming that these consumers who potentially will buy these bonds are not consuming that, interest rates are possibly going to increase, and that's why they're increasing, right? So if you sort of ignore that, they're like, oh, wow, these bonds are actually very, very worth the investment, maybe. Right, so that's one reason why you might see the redemption values bigger than the face values. So what do we have here? So somebody is selling this bond, or maybe we're going to buy this bond from a consumer. Keep in mind the bond has a face value of 500. So you should typically not be paying more than that 500, and definitely not pay more than 800. Else, what's the point? So let's suppose we pay, let's give them at least something close to 500. Let's assume P is 400. I just want that number to be a little bit more extreme so you can sort of see what's going on here, right? So if this is how much we pay, and let's assume that this is, of course, at time t is equal to 0, then what would be the present book value under the interest rate I for this particular bond? Well, again, that's going to be equal to c divided by I times 1 minus nu to the power of m plus c times nu to the power of n. And once you use our interest rate of 1.9% and n is equal to 24, c is equal to 10.5, and then why is that c there? That should be equal to r. You should get something approximately equal to $710.09 as the present book value of that bond. So we paid $400 today, and the present value of this bond under the anticipated interest rate I is $710. So what we have here is an unrealized gain. It's what some people refer to as an unrealized gain of what? So that's just going to be equal to our book value, time t is equal to 0 under I, minus the price we pay, and that's going to be equal to $310.09. And that obviously is really good. So how can we interpret this number? So obviously the higher that number is, the better off it looks like to us. So that means this is likely to be a good investment, assuming that the interest rates do not just go crazy by the time we do get our redemption value, right? So once we pay our $400, what will be the yield rate for this transaction? So the yield rate, keep in mind, so yield rate is the interest rate J that satisfies BP is equal to BVJ t is equal to 0. Obviously, if our unrealized gain is high, we would hope to see that our J is high as well. So what is a high yield rate with respect to this particular type of unrealized gain? So the equation we seek to solve is going to be 400 is equal to 10.5 divided by J times 1 minus 1 over 1 plus J to the power of 24 plus 800 divided by 1 plus J to the power of 24. So one thing you can do is you can define this right-hand side to be equal to, say, f of J. And what you're going to see is this curve will always be a decreasing curve, as described earlier. And what we would need to do is we need to set this equal to 400. So 400 is going to be there. And what we seek to find is this number J that we desire, right? So using graphical analytical methods or some other fancy calculus tricks you may know, one can find that J will be approximately 0.04901 or approximately 4.9%. Right? So obviously the larger that yield rate is, the better it is for us in terms of its purchase. Now I just want to give you a couple other prices. So let's assume that we buy this loan at, for example, instead of 400, maybe we buy it for 300, cheaper, 200, even cheaper, and 100, even cheaper than that. Then solving those three equations, you will see that, well, what do you think will happen to the yield rate? Well, obviously it should go up. So from 400, so this is for $400. If you decrease the price to 300, that is, we manage to save more money, that's going to give us a yield rate of 6.5%, and then 9.1%, and finally 14.6%. Right? So obviously it is not a linear growth, it is a geometric growth, but that gives you some ideas of the yield rates that you could achieve with these particular prices if you happen to manage to buy that bond for those low prices. Now that we know the basics of bonds, I just want to take the moment and briefly introduce a couple types of bonds that are viewed as special types. Some are common, some are not as common, but it gives you a couple of variations to sort of understand what you could do with your bond structures, especially if you are a bond issuer. The first is a zero coupon bond. And what exactly is that? Well, this is extremely common for short-term debt of companies. Debt, D-E-B-T, of companies. right? Short little ventures. So what exactly is a zero coupon bond? Well, it is precisely what it says. It just means that each of our coupons is going to be equal to $0, and this is going to be true for k is equal to 0, 1, 2, all the way down to m. So if this is the case, then what does that mean for our formulas? So that means the BV at t is equal to 0 under I is going to be equal to what? So that's just going to be equal to 0 times ANI plus our redemption value nu to the power of m. And 0 times anything is just going to be equal to 0. And then we're just going to be left with our VN, or R nu m. So that means our yield rate equation, which keep in mind is just P is equal to our book value present under some rate J, is just going to be equal to what? Well, that's just going to be equal to R all over 1 plus J to the power of m. And this is actually very, very easy to solve. So let's just actually go ahead and solve this. So that's going to be equal to what? So divide both sides by R and reciprocate. So we're going to have R divided by P is equal to 1 plus J to the power of m. So that means our yield rate J will just be equal to the nth root of R divided by P minus 1. So we get this nice little relation for solving for our yield rate under zero coupon bonds. So the mathematics definitely is easier. And what must be true for this redemption value R? Well, obviously in this particular case, if R and P are equal, that quotient will be equal to 1. The nth root of 1 is 1, and 1 minus 1 is 0. But isn't it common for redemption values and face values to be equal to one another? Possibly. But obviously, if you lend somebody $500 today and they only give you $500 5 years later, that doesn't really make sense. So redemption values are, at time t is equal to n, are typically larger than the face values, right? F. That is, R is typically greater than F. Else, what's the point, right? Because if I give you $500 today, you should be able to turn that $500 into something a lot more, alpha to the power of n, right? Whatever that effective accumulated value would be, right? So if I only give you $500 at time t is equal to n, you've lost money technically, because I've just given you that back, and you should have been able to turn that into 500 alpha to the power of m, right? So that's obviously a loss. It's a loss in most cases anyway, right? Because most people should be able to do at least one transaction in that time. So that's one special type of bond, which we call a zero coupon bond. So another type of bond that I've already mentioned is called par value bonds. And par value bonds are just bonds with F is equal to R. So face value and redemption value being equal to each other. Now, nothing really exciting happens with our formula, because keep in mind generally, let's do the price. So P will be equal to C divided by J times 1 minus nu J to the power of m plus R times nu J to the power of n. So this is obviously the general version of that. But under a par value bond, right? So if F is equal to R, then what do we have? So this is equal to F now. So we have C divided by J times 1 minus nu J to the power of m plus F times nu J to the power of m. But keep in mind, C is also calculated with respect to F as well. So this is going to be equal to RCF all over J times 1 minus nu J to the power of n plus F times nu Jn. Right, so this is for par value bonds. You could factor out an F here, but nothing really special is going to happen. But one modification that one could do is choose RC to be equal to your yield rate. Or you could choose P such that J is equal to RC. Because we already know what RC is, because we already know what our coupon payments are going to be for this particular bond. So we can reverse engineer that equation to find out what P, or how much should we buy this bond for, in order for the yield rate to be equal to the coupon rate. So when you do that, a lot of simplification actually happens under that. So that's just going to be JF all over J, 1 minus nu J to the power of M, plus F nu J to the power of M. And notice that those J's will cancel, so let's actually distribute that Fn. So we're going to have F minus F nu Jn plus F nu Jn. And when you have that, you're just going to be left with F. And keep in mind this was the equation for P. Right? So when you choose RC is equal to J, you get this particular relation. Right? So this is just some special designs or choices. Not necessarily common, but definitely could, and those are the conclusions that you would get. So we can get some theorems immediately from this conclusion, and those are the following. So if the coupon rate is equal to the yield rate and the face value is equal to the redemption value, then the price you had paid for that loan is just going to be equal to the face value. That's the first thing. The second thing that we conclude is the following. If our price that we pay is equal to the face value, and let's actually choose if RC is equal to J, and let's say P is equal to F. Actually, if P is equal to F, and let's say F is equal to R. F is equal to R, right? So if the face value is equal to the redemption value, so it's a par value loan or a par value bond, and we pay the bond at the price value of the face value, then what you're going to have as a conclusion is that RC will be equal to J. So it's almost like an if and only if scenario. So it kind of goes backwards. So these three scenarios are pretty much equivalent to one another, right? So those are called some par value bonds and zero coupon bonds. Let's describe a couple more. So the next type of bond actually isn't about bonds, but bonds when they interact with a transaction such as a purchase. So let's assume that we buy a bond under some yield rate J. And then there's going to be some associated book value under that rate J, which is going to be associated to the price for which we paid P. So if that price is greater than the redemption value, then we say that that bond is purchased as a maturity premium bond. Now, some people will define premium bonds by comparing the price for which you pay versus the face value. That would be an upfront premium bond, but a lot of people usually, well, I wouldn't say a lot of people, but some people prefer to price bonds with respect to their maturity in the future rather than today, right? Because we can always do what we did earlier and just look at the present value of the bond and then compare to that of the price and see if we have that profit or that dividend or that differential between the price and the book value yield, right? So if we have this particular equation that P is greater than R, then we say that this is a maturity premium bond. So once we have a maturity premium bond, then we can start defining a couple concepts. The first concept that we're going to define is the premium. So the premium will just be equal to BVJ, aka P, minus R, right? Because if BVJ is bigger than R, that means BVJ minus R should be a positive number. And what is that going to be? So that's going to be equal to CANJ plus R nu JN minus R, generally speaking. And we can do some cute math to this, or you can leave it as so. But technically speaking, once the formula is simplified, it's actually a little bit more easier to use. So this is going to be equal to what? So what is C? Well, C is just going to be equal to C times RC, and then A and J is just going to be 1 over J times 1 minus nu J to the power of M. And then we're going to have our R nu J to the power of N minus R. So once we have this, what else are we going to have? So let's just take a look. So what do we got? So if I factor out an r out of this tail end, so I'm going to leave the front the same, so f r c over j times 1 minus nu j to the power of m. If I factor out a minus r, and then write nu j times nu to the power of n as our typical j reciprocal kind of then, what are we going to have? So this is going to be equal to rj over j. So technically I haven't done anything. And then I'm going to be left with 1 minus nu j to the power of m. Now, the only reason why I multiply top and bottom of this equation by j is because notice that I have something very, very in common here. In particular, I have this term here and this term here, which is just a present value of an annuity immediate. So what am I going to be left with? So I'm going to be left with RCF from the first term, and then I'm going to be left with JR in the last term, and then I'm going to be left with ANJ in the common term between the two, right? So this is one formula that a lot of people use to calculate the premium, if it is a premium bond, of an associated maturity premium bond transaction. Now, another thing that I want to define, and this is sometimes used in transactional analysis, is called the modified coupon rate. So this is the modified coupon rate. So just some more fancy math. And this is just going to be defined to be equal to RCF all over R. And from this modified coupon rate, you can actually get a couple sometimes useful theorems. So the next theorem that I want to mention are the following. So theorem 3, if BVJ times t is equal to 0 is greater than R, that is, it's a maturity premium bond transaction, then RCF will be equal to JC. And also it goes the other way around. So this is actually an if and only if statement. So this is true if and only if this is true. So what is this? So this is our premium bond. So our bond will be premium if and only if this inequality satisfied. And equivalently, if we use our modified coupon rate to sort of compare, we can say that a bond is premium. And I suggest you rearrange this last inequality in terms of this modified coupon rate, that this is true if and only if RCM is greater than our yield rate, J. Right? So we get these two important theorems as well. Right? Now, another theorem that I want to mention, let's call it theorem number 5, says the following. If a bond is premium and redeemable, that doesn't look like redeemable, too many E's, redeemable at par, then RC will be greater than J, or equivalently, BVJ will be bigger than F. Right? So we have those immediate inequalities, combine all the things that we've discussed up to this point. Now another type of bond, in addition to maturity premium bond, is the following, and this is called a maturity discount bond. And you probably can take a guess of what this is going to be. So this is just going to be a bond with BVJ that is, take a guess, this is going to be one that is less than R. Right? Premium will be bigger than R, discount will be less than R. Right? So then one can define discount, the discount of this discount bond transaction, to be equal to R minus BVJ. T is equal to 0, right? Because R is the bigger one of the two, so R minus BV will be a positive number, and I highly suggest you try on your own to verify that this is equal to, almost like the reversal of the other equation, but it's going to be equal to J, our yield rate, times the redemption value, minus RC, our coupon rate, times the face value, times A and J, our annuity immediate, under our yield rate, J. Right? So that's what we refer to as the discount of the maturity discount bond transaction. Right? So those are just some of the basics that you definitely should know when it comes to dealing with bonds. We'll discuss a couple more important bond principles in the upcoming video, and I hope to see you then. Take care.